Morning, everyone. How are you? Ready for linear algebra? Yeah, linear algebra is very interesting topic. But when I started to learn it, and it was first semester in my university, when we learned linear algebra, I really hated it. Now I'm teaching it, so it's like if you still hate it, that's okay. In a few years, you will love it because you will use it everywhere, so you will get used to it. And as people say about mathematics in general, you cannot understand it, but you can get used to it. Okay, so this is the purpose. You just need to do more of it, and then you will get used to it. And then you will find it appealing, interesting, and obvious almost, because when you just start to learn linear algebra, it sounds like very abstract things. You have multidimensional spaces, you have all kind of difficult, complex terminology. Then you have all kind of weird rules, which you do not understand why they invented these rules at all. But then you get used to it and you say, like, this is obvious, this is basic stuff. You don't even need to memorize it anymore, right? Because you trained yourself to remember it somehow. So turn on the microphone. Okay, so hopefully by now you already understand that we will work a lot with linear algebra because you saw state space systems and we have matrices there, vectors, derivatives of all kinds of vectors and other things of that kind. So all of that course will be based on linear algebra. We will do a lot of it. And now I will try to squeeze entire course of linear algebra in 1 week lecture, which is almost impossible task. So I assume that all of you already somehow heard about linear algebra and know something about linear algebra. So you have some experience with linear algebra and you multiply different vectors, matrices, and things of that kind. So when I'm saying matrix, you know what I'm talking about. And this is not the first time you hear it. If this is the first time you hear it, please raise your hand. Everybody saw matrices before. That's great. All right, so I will go very fast through terminology, through all kind of theorems, through all kind of rules that you have in linear algebra, different types of multiplications, to get to eigenvalues, because all of that we kind of run fast through will be useful for computing eigenvalues. And eigenvalues will be extremely helpful for that course. That entire course is based on eigenvalues of this matrices A that I showed you in state space. All of the properties of our systems will be dependent on the eigenvalues of this particular matrices. Okay, everything we will be doing will be related to this eigenvalues, and I will connect it later in future lectures how it relates to all of these eigenvalues and why this is so important. But now you need just to focus, and I will again jump fast through all kind of topics, and I will stop in particular on particular things which are more important for that course. Okay. And you can read through the lecture notes and you have videos. I will publish also that video online. So you will get back to that video when you need it. Like if you don't remember something or you want to look for some rules, theorems and whatever from linear algebra, you can back to the slides and this lecture when you need it for your homework, for your assignments, for your project, and so on and so on. So again, if I'm going too fast, you can also stop me. If you have some questions, please stop me in the middle and let me know, okay? Because this is very important that you will get the background, the most important things from linear algebra. Otherwise, it will be very difficult to work through the other material in that course. So stop me anytime you have some questions, all right? Okay, so we will talk probably half of that lecture about halfway here, okay? Hopefully we'll get to eigenvalues, but we'll see. And I will talk about nomenclature, how I define different variables, names of the variables, what are typical names of the variables that I will be using in that course. I will talk about multiplications, transposes of the matrices, rank, determinant, all of the inverse matrices, and so on and so on, all of the basic linear algebra that you typically learn in the first course on linear algebra. And we will get also to solving system of linear equations. Typically, people actually start with solving system of linear equations, but I don't like that approach when you start with linear equations because you need to know a lot of stuff before you get there. So it's much more convenient to solve them in a different way, not using the typical ways that you learn in linear algebra, which is the like reduced echelon row or something like that. So you have technically easier ways to do that when you know determinants and so on. Okay. Now, the techniques that I will be explaining here are not the most optimal or simple techniques to solve the problem numerically. The reason is that we will be working mainly with matrices of order 2 or order 3, sometimes order 4 maybe. We want to solve all of the questions and problems by hand, which means I want to show you the actual process of computation of each one of the eigenvalues or other things, which means that I cannot do that on matrix 10 by 10, right? I cannot solve polynomials of 10th order by hand. All of that is numerical, so I cannot handle matrices of higher order. So all of the examples will be of second or third order typically. You can do exactly the same thing with higher orders if you understand the technique, right? So if you learn how the process works, you can repeat the same process on just higher order matrices. But the examples are easier to provide on lower order matrices. So pay attention that I'm using specifically all of the tools which are very convenient for lower order matrix. For example, if you know what determinant is, computation of determinant for the matrix is some sort of complex operation, especially for higher orders. So finding determinant of very big matrix, like 100 by 100, it's very complex computation, okay? Because you need to recursively go to lower order determinants. So for example, 100 by 100 determinant is sum of 199th order determinants. And each one of these 99th order determinants is sum of 99 98th order determinants, and so on. So if you kind of build that sequence of computations that you actually need to do, it's huge. But for matrix 2 by 2, it's just one line, okay? For 3 by 3, maybe a few lines that you need to write down, okay? It's just sum of 3 determinants of 2 by 2. That's it. This is that simple. Especially if you have zeros in the matrix, this becomes very easy then. So for that type of thing, it's easier to use determinants for almost everything. For higher order matrices, you typically do not want to use any determinants for anything computationally. It's too expensive. So computational determinants of higher order is very expensive, even for computers. And they become more and more prone to numerical errors when you compute them. Because higher the order is, more numerical issues you might have with them because of the approximation in the computer that you're doing, like rounding some particular numbers. So you have issues that I'm not mentioning here in that course, but you just need to be aware that they exist, okay? So you not always can extrapolate all of the techniques that we are using here for hand computation, for numerical computations as well of linear algebra. And for that, you have special course, numerical methods. Okay, there you learn all these techniques of what is more optimal to do on the computer. This is a separate course. Any questions so far? All right, so we'll be using all kinds of scalar values, which are just single number, complex number, or real number. And I will call them A, B, C, not capital letters, regular letters, okay? Or alpha, beta, gamma, and so on. All of the Greek letters will be just constants of some kind. And then you have dimensions, and they will be typically N, M, P, or Q if you need more. Okay, so this will be the letters that I'm typically using for dimensions of matrices. And first dimension will be always the dimension of rows, and second dimension will be dimension of columns of the matrix, okay? Sometimes I'm using capital N, sometimes I'm using regular N, but NM typically will tell you about dimensions, some vectors or matrices. Indices of particular coefficients inside the vectors or matrices, I will call them I, J, K, L letters. These are typical letters which are used for just indices, which is location of that thing, that number in the matrix or vector. Vectors will be U, V, W, X, Y, and for Laplace transform of these vectors, I will use X, U, W, like capital letters with S, right? Matrices will be typically A, B, C, D, like beginning of the alphabet, right? Transfer functions will be typically G and H, as we used in the previous lecture. So these are typical letters. If I use Laplace transform, I use S variable. If I'm using Z transform, which is for discrete time systems, I'm using Z variable. These are standard letters for Z transforms and S transforms, Laplace transforms. Also, we will talk a little bit about transformations, and transformations will be typically denoted by T or P. Okay, these are variables that we are using for, they are also matrices, but they're special matrices in some way. They are transforming some other matrices. For example, for diagonalization, you are using T transform, which is diagonalizing the matrix into diagonal form. We'll talk about that a little bit. Any questions about notation? Okay, so yes, sure.
So can you go back? So you have as vectors, you have x of s. So that is a vector of Laplace.
It could be like x1,
So
s, x2, s, x3s, vector,
Okay.
x of s.
And you put it,
And Laplace transform of matrices or vectors is like Laplace transform of each element separately.
okay. And you've indicated that it's cap. I think I don't understand why that's capitalized in the vectors.
So these vectors are vectors of time typically.
Yeah.
So this x of t, y of t, w of t. These are vectors in Laplace domain. So Laplace,
Capitalizing like they were matrices.
they are still vectors. They're not
Okay.
matrices.
Okay.
So the point is that Laplace transform typically in signals and systems we denote with capital letters. So like y of s, u of s, when you draw in like transfer functions like g of s, all of them are capital letters.
Yeah.
But we also use capital letters for matrices. So when I'm using capital letter with s, yes, so when I'm using the s, this is still vector, but for Laplace transform. And that's why it is capital letter here.
Thank you.
This is the, just to differentiate between matrices and Laplace transforms of vectors. Right. Okay, so we know from geometry, we know what vectors are, and vectors are just particular point in space. If you have two-dimensional space, you have coordinates of a point which are two numbers, x1 and x2, some kind, right? Like this point is 2, 5, for example, right? And this is from origin to that point, you draw an arrow, which is pointing to that point in space. In three-dimensional space, you have three numbers, which describe the three-dimensional space, right? And you have vector, which is pointing from origin to that x1, x2, x3 point, which are coordinates of that particular vector, and it will look like that. So this is like 3, 3, 5. So have one is 3, another direction is 3, and height is 5. But linear algebra is generalizing that notion of vectors in n-dimensional spaces. You still can use 2 numbers, 3 numbers for 2 and 3-dimensional spaces, but you can use 4 numbers, 5 numbers, 10 numbers, 100 numbers, whatever size of the vector you want, okay? So linear algebra vector is practically generalization of regular vector, geometric vector, physics vector, but in n-dimensional spaces. So if your dimension is n, and you have n real numbers or complex numbers in that case, you can just draw them as a bunch of numbers, okay? And this is called vector in linear algebra. Now, typically we are talking about column vector and not row vector. So if I'm saying vector, I always mean column vector and not row vector. This is standard way to define vectors in linear algebra. You never draw them in line, you always drawing them as column, okay, not as row. Now, the meaning of that notation, r to the power of n, is just n numbers, which all of them are real n real numbers. So kind of multiplying r by r by r by r n times. So you get r to the power of n. This is a notation of sets, which says that this vector belongs to that set. Now, matrix is table of numbers, which has 2 dimensions, n and m. So m rows and columns. Typically, this is how we define matrices. An element of the matrix will be a, I, j. Again, row I, j column. So elements will be denoted by ij. These are indices of the matrix. Okay, so you have like 2, 1. So I equals to 2, j equals to 1. So like A21 is second row, first column. and so on. So each one of them will have their own index, and you will build the matrix from these elements, and they just some numbers, complex numbers or real numbers. We will work only with real numbers. They could be also complex numbers. Any questions so far?
In this nomenclature, if you had a four-dimensional matrix, is that?
So it
not
will
a
be
matrix
4 by
anymore?
4.
You don't call it a matrix anymore?
It is matrix. 4
Yeah,
by
but
4.
it's- Oh, an n by n by,
So m might be equal to n equal to 4.
right. I'm just asking about nomenclature, if I had like a thing that I would call a matrix in MATLAB, which would be like m by n by p by q by z.
This is
So it's
tensor.
many dimensional.
This
You
is
call it
tensor.
Okay, thank you.
This is tensor, yes. So when you have multi-dimensional matrices where you have like third dimension and fourth dimension and so on, it's like multi-dimensional array in programming. If you wish, this is in math, it's called tensor. But matrices are also always two-dimensional. You have only two sizes, okay, 2 dimensions, m and n. All right, transpose means you just switching between rows and columns. That's it. So if you have row vector, transpose of that vector is column vector, same vector, but column, and the other way around. If it is matrix, you just flip it over main diagonal. So you're flipping I and j. You're flipping the indices. So I becomes j and j becomes I. This is transpose. This is very simple manipulation, just switching by the main diagonal, kind of flipping rows and columns, okay? Flipping over main diagonal of the matrix. This transpose operator, and typically we are drawing that as superscript t to whatever vector or matrix you have. This thing means that you're just flipping rows and columns. Diagonal matrices, we have a few special matrices that we'll be working with a lot. And these are diagonal matrices where you have zeros everywhere except the main diagonal. And my main diagonal might have zeros, but it doesn't have to, okay? So when I'm saying that main diagonal is not zero, it does not mean that you cannot have zeros on main diagonal. It still will be diagonal. If like entire zero matrix, it's still diagonal matrix with all zeros on the main diagonal, but it doesn't have to be. So you might have some other numbers here on the main diagonal, okay, of the matrix. Everything else here is zero, and here is also zero. Very special matrix is identity matrix, is when all of the diagonal is ones. So you have only ones on the main diagonal, this is identity matrix. Upper triangular matrix means that you have all of the zeros here and something here. It could be anything practically, but maybe not zero. Upper triangular means that you have like upper triangle is filled with some numbers and bottom triangle of the matrix is zeros. And same thing for lower triangular matrix, which is the opposite. Like bottom part is filled with some numbers, including the diagonal, and upper above the main diagonal, all zeros. This is lower triangular matrix. So you'll have some of these matrices, they have very nice properties. For example, all of the triangular matrices have their eigenvalues on the main diagonal. Very easy to find. You don't need to compute anything. They all sit on the main diagonal. For all triangular or diagonal matrices, just look at the diagonals, these are eigenvalues. And block triangular matrix is also very important for us. We will not use it too much, but this means that you have blocks which are sitting on the main diagonal, and they all triangular in some sense, okay? So they kind of block triangular. You have, again, for example, zeros here, something here, one block, let's say Z block here, and Z block there, okay? So you might have some number here, you might have some number here, here you might have some numbers, but here you have zeros and here you have zeros, like around the block. Like you have multiple blocks in the matrix. So you can divide it into multiple sub-blocks. Why is that important? Because again, eigenvalues of block triangular matrices are eigenvalues of the blocks on the main diagonal. That's all you need to know about it, okay? So if this is like 2 by 2 block, you're just finding eigenvalues of the 2 by 2 matrix. And these are eigenvalues of a bigger matrix, which includes that block. So it's kind of much more convenient to see how the system is organized dynamically. I will try to give also some insights later when we get to that. Addition and subtraction of matrices or vectors is extremely simple. It's just element by element. This also means that they need to have exactly the same dimensions. Otherwise, you cannot add or subtract matrices. So if you add or subtract two matrices or vectors, they need to be exactly the same dimensions. Which means that if you have like column vector and row vector, you cannot add them, subtract them. You need to transpose one of them first, and then you can add them, right? They need to have exactly the same dimensions. And this is element by element, so it's very simple. But for multiplication, we have multiple different types of multiplication, and this is just short list. You have many more multiplications. You have Kronecker, Adamar, and more, okay? But these are the types that we will be using in that course typically, okay? So one type is multiplication by just scalar value, which means multiplying by some constant, vector or matrix. Another type, multiplying vector by vector. Third type, multiplying matrix by vector. And fourth type, matrix by matrix. So I have four different types. So how they are different? Let's see. So what is their meaning? First of all, of multiplication of particular vector. So you have vector, which is n-dimensional. Here I'm drawing it, obviously two-dimensional, but you can try to imagine n-dimensional vector, which is just a bunch of numbers. Technically, multiplication of the vector by scalar means just stretching the vector by that number. If scalar is positive, you're stretching that in the same direction. If scalar is negative, you're stretching that in opposite direction. Okay? So the value of that number by which you multiply is how much you stretch the vector, squeeze maybe, if it is between 0 and 1. Okay? It's just by how much you multiply that entire length of the vector. And sign is in which direction it will go. For positive sign, it will go with the same direction it was the original vector direction, okay? But if it is negative sign, you flip in the direction into opposite side. All right, any questions about that? Okay, so here's one example. You're just taking vector 1, 2, 3. You multiply each element by 5, which is a scalar multiplication, and you get some other vector. Same thing for matrices. You just multiplying each element by that number, and you get output. Practically, it means you just scaling that vector and making it longer. Now, vector multiplication, you cannot really do vector by vector multiplication, but you can do something which is called dot product or inner product sometimes. So inner product is multiplication of element by element, and they also need to have the same dimension, vectors of the same dimension. You multiply them element by element, and then you add them, these multiplications together. So you get a single number, so it's scalar. The output of vector by vector multiplication is one number, okay? You're just taking, for example, you have vector A and vector B. You're just taking elements of vector A, which is A1, A2, AN, and elements of vector B, which is B1, B2, B3, and so on, until Bn. You multiply them pairwise, and then you add them together, right? This is dot product, dot multiplication of two vectors. So here's one example. You have vector 1, 2, 3 multiplied by 4, 5, 6. Multiply 1 by 4 plus 2 by 5 plus 3 by 6. You get 32. All right? This is dot multiplication. Any questions about the technique, how you compute it? In the next slide, I will get what it means. Like, why do we even need it? It's a very important function. We will use it all the time. Any questions so far? Okay, you have multiple different nice properties of dot product. I'm not going through all these properties. This is regular distributivity of the product, associativity, and all other properties. This one is important. So you can write dot product as A transpose times B, assuming that both of them are column vectors, which means you have two vectors like that. A transpose will look like that. So now you can multiply this vector by that vector as you multiply matrices or vectors, element by element. And this will be that element by the first element here, plus second element by the second element here, and so on and so on. You'll get exactly dot product. So A transpose B, or B transpose A, which is the same thing, will be that dot product. So sometimes it's more convenient to write it that way instead of actual dot. And I denote dot product with actual dot, which is visible. It's not like regular multiplication AB, it's like A dot B, like thick dot, right? Now some caution here, because people typically do mistakes with how they cancel stuff in linear algebra, and this is very dangerous stuff in linear algebra. Never cancel anything, okay? Forget about canceling, because you're used to regular algebra, you can cancel variables if they're the same, if you divide by particular variable, or if you have common multiplier on both sides of the equation, you just cancel it. No, you cannot do that in linear algebra, okay? No cancellations whatsoever in linear algebra. You're doing that in a completely different way. Why is that? So here is one interesting example. What I'm saying is if A dot B equals to A dot C, right? That kind of equation. Let's say this is true. Then A dot B minus C based on that rule will be equal to 0. Typically people say, oh, then this means that A equals to 0 vector, or B minus C equals to 0 vector, which means B equals to C, right? Not at all. None of the above. Okay, here's an example. Why this is not true for that case. So you cannot actually cancel A here. So B is not equals to C. So A equals to 1, 1. It's obviously not 0. And B equals to 0, 1, and C equals to 1, 0. Obviously, B is not equal to C, right? They do not equal. And this is not 0. But A dot B equals to 1, and A dot C equals to 1. So this is true, and this is true. But none of these things is true. Okay? So B is not equal to C, and A is not 0. But the multiplication is 0. So you need to be very careful when you are thinking to cancel anything. There are other ways to do that, okay? And we will see these ways a little bit later. So what is the meaning, geometric meaning of dot product? It's very important that you will have that intuition a little bit, because we will do a lot of linear algebra and you might forget about what it means. So it's easier to remember that geometrically. Dot product means some sort of projection of one vector onto another vector. So projection is that kind of direction. So you're projecting, for example, vector x and vector y geometrically. So the result will be size of that vector times size of that vector multiplied by cosine between them. This is a dot product, okay, in 2 dimensions. Now, it's also true for any number of dimensions, but it's more difficult to define what cosine means in more than 3 dimensions. Okay, in 3 dimensions, you can still think about cosine between vectors which are in 3 dimensions in space somewhere, right? But for 4 dimensions, what is even cosine? So it's more difficult to define. And technically, it's defined through the dot product, so it's circular. So it makes no sense. But in 2 and 3 dimensions, it's easy to imagine what it means. So what does it mean to multiply by cosine of the angle? It means you are taking the length of the projection and vector in that direction, okay, and multiplying by that direction. So you have size of vector y multiplied by the projection. So it's practically y multiplied by the coefficient, whatever the coefficient is here, okay? So it's projection in the direction of y. But you can do the same thing in direction of x. So you can make perpendicular line here, right, to that vector. So it will be that thing multiplied by vector x. That length up to that projected point here, multiplied by vector x. You will get exactly the same thing, okay? Because we are talking about absolute value here, not direction. Dot product has no direction. It's scalar number. It's not vector. So the value of that vector is size of the projection times size of y, or times of y projection times the size of x. This is the meaning of dot product. The most important property from that you need to get, that if they are perpendicular, the vectors are perpendicular, the projection is obviously 0, right? So if you project a perpendicular vector onto another vector, the size of that vector, of projection vector, is 0. So 0 times anything is still 0. So dot product of perpendicular vectors is by definition 0, all right? And this is even definition of perpendicular for n-dimensional spaces. The dot product is 0, all right? But it's true for 2-dimensional, 3-dimensional, and so on. Any questions on that? So that's what you need to remember out of dot product. The dot product of perpendicular vectors, orthogonal vectors, whatever you call it, is zero. Very important property. Now, multiplication of matrix by vector. And I assume that you've seen one of these ways to multiply vector by matrix. And maybe you haven't seen another one, which is also extremely useful, especially in machine learning and other domains, where you can think about intuition, what it means. So what it means, multiplication of the matrix by a vector. Do you know what that means? What the intuition behind it, what matrix does to a vector? Let's say you have two-dimensional vector and two-dimensional matrix, 2 by 2. What does it do to that vector? Like you have particular vector, you multiply it by some 2 by 2 matrix. So what this matrix does to that point in two-dimensional space? Intuition about matrix multiplication, what it means. I mean, you have obvious answer here. It moves it somewhere, right? Like you'll get another vector. If you multiply matrix by a vector, you get another vector. So this vector will be same vector or different from the original vector. So it will be some other point in space, right? But do you have any additional intuition? What happens to that point? So you can think about that matrix as transforming that vector from one vector into another vector. But this transform could be thought also, I don't know if you learned that in linear algebra course, but typically you can think about that as multiple different operations. So this could rotate the vector, it could scale the vector, it could share the space somehow, kind of a thin modification of the space. So what happens is you technically modifying the space itself. So you have rectangular coordinates. What matrix does, multiplication by matrix, it converts it into some other coordinates, which could be rotated, scaled like that, and shared like that, and doing all kind of modifications on the space itself. And depends on that, this vector just becomes in different coordinates. So it kind of transforms system of coordinates of the vector. It modifies system of coordinates, including, again, rotation, scaling, and so on. Okay. Same thing happens with n-dimensional matrices and n-dimensional spaces. You're kind of squeezing, rotating, and manipulating the space, and this vector becomes kind of getting new coordinates, right? Coordinate space. So matrix is changing coordinate space for the vector. You're just practically renaming these coordinates into something else. Based on the matrix, you'll have different things. And this is very important connection also to what eigenvalues are doing and eigenvectors. What happens to eigenvectors when you manipulate in particular multiplication of matrix by eigenvector? Because we will see later what it does to eigenvectors specifically. But this is a standard way to multiply matrix by vector. You're typically taking first row and making dot product with the vector x. So this is matrix A times vector x is dot product with the first row and that column, then second row dot product with the column, and so on. So you're taking each row, multiplying element by element, adding them all together, and you get the element, the first element, and then you get the second element, which is second row here, until you get to the last row, which is like last row dot product with that column. Okay, this is standard matrix manipulation to multiply matrix by vector. Remember that part? Or too long ago? Need example of that? Who needs examples of multiplying matrix by vector? Okay, so let's multiply vector by matrix. So have Okay, let's say you have matrix, multiplying it by vector. Let's make it not square. Okay. Pay attention, the multiplication is always to match the dimensions. So if this is like m by n, this must be n by 1, because it's vector. And this dimension must be equal to this dimension, otherwise you cannot multiply. This is number 1. The output will be also n by 1, same dimension. So let's say this is matrix 3 by 2. So it will be 1, 2, 3, 4, 5, 6. And here we'll have 1 and 2. What happened? So you're taking, first of all, computing the first element in that vector. So this is also like 2 by 1. So this must be also 2 by 1. So I'm taking first row. No. This will be 2 by 1. So this must be the external one by this one. So this will be a little bit long. 3 by 1. So taking 1 times 1 plus 2 times 2. Then you get into the second row, which is 3 times 1 plus 4 times 2. Then you get to the third one, which is 5 times 1 plus 6 times 2. All right. That's it. Then you add, and you get 5, so 3 plus 8, 11, 5 plus 12, 17. This is the vector. Right? But this is not the only way to look at multiplication of matrix by a vector. And sometimes more convenient way is to think about that as weighted sum of columns of A. So here is how you look at that. So this is weight x1 times the first column vector plus weight x2 times the second column of matrix A. And so on until you get to weight xn times the last column of matrix A. Okay? So you can see the same thing here. It's practically 1 times that column plus 2 times that column. You'll get practically the same thing. Right, so it's 1 times 1, 3, 5 plus twice 2, 4, 6.
Can I ask
For
just another
the same thing. Yes.
So, the vector that you got there, 1, 2, shouldn't that be written as a row vector because it's 2 by 1 in order to multiply? Or is that?
No. So the inner dimension should be the same. So it's 2 and 2. So it's 2 rows, 1 column.
Oh, yeah. Thank you. Thank you.
The first dimension is always rows. Okay. So compute is like 4, 8, 12 plus 1, 3, 5. You hopefully get the same thing. And as I discussed, the meaning of the transformation is basically squeezing the space a little bit in multiple different ways, including rotation, scaling, and so on. This is multiplication of, any questions before that? Before multiplication of 2 matrices? Okay, multiplication of 2 matrices technically is very simple. It's multiplication of matrix by the first column of the second matrix, then by the second column, and so on. So you get again, matrix, and dimensions of this matrix will be accordingly to that thing. It will be very similar to that thing. So it will be m by n, and then it will be n by p. So the result will be m by p. Okay, this is how dimensions work, always. And again, inner dimensions must be the same. Otherwise, you cannot multiply two matrices. They need to match. So you can multiply, if you have like matrix of m1 by n1 dimensions, and then you have another matrix which is m2 by n2 dimensions, n1 must be equal to m2, and the result will be m1 by n2. Right, this is how it works. And again, you just multiply first row by first column, first row by second column, first row by third column, and you get these three numbers, and then you get this row by this column, this row by this column, and so on, and you get the second row. Okay, it's just all of the cross multiplications, all of the dot products between particular row, row I, and column J in the matrix B. This will be element ij of the multiplication. This is still dot product between the row I in matrix A and column J in matrix B. This is element ij of the multiplication. Any questions on that? And you have million of different properties of multiplication. Again, I'm not going through all of these properties. You have only a few important ones here for us, for our course. First of all, multiplication, you cannot switch the order. Not in linear algebra, not like in regular algebra. So AB is not always equal to BA for two different matrices. Here's one example. You have one matrix times another matrix, and then I'm just switching the order of the matrices, and multiplication is completely different, not even similar. Okay? You don't have anything in common. So you cannot switch the order of multiplication. This generates additional issue here. So you always need to remember if you're multiplying by a matrix from the left or from the right. This will be different things. You need always to be consistent. So if you multiply, for example, you have some equation with matrices. If you multiply that equation from the left by some matrix, the other part of that equation still needs to be multiplied from the left. But if you multiply by the same matrix from the right, the other side needs to be multiplied from the right. Otherwise, it will not be correct. You cannot multiply like one left and one right. This will not work. This is not the same thing. Okay, so remember, you have left multiplication by matrix, and you have right multiplication by matrix. They are different, not the same thing. Additional important property here is this one, that if you doing transpose, which is a flipping rows and columns of multiplication, this switches the order of the matrices, which means AB transpose equals B transpose times A transpose. All right, this is switching the order of the matrices, very important. And this is true only if multiplication exists, obviously. So I'm typically not saying that, but this is always true. Okay, you need always to remember that the multiplication needs to exist first. You cannot do that for anything. All right, another thing that you need to remember is trace. We will use it from time to time. Trace is just sum of diagonal elements of the matrix A. And you have some very convenient properties, which is trace of sum equals to sum of traces, and multiplication of AB trace, which is trace of the multiplication of two matrices. You can switch the multiplication inside the trace. So trace of AB equals to trace of BA. Technically, AB is not equal to BA. For example, it could be, let's say you have vector like Z multiplied by vector like Z. So you'll get just number, right? Because vector like Z multiplied by vector like Z will give you number. Okay, so this is like that. Okay, from your side. So this is vector of row multiplied by vector of column. It's just dot product between those two vectors. So this is number. But if you multiply Z vector by Z vector as matrices, this is n by n matrix. Okay, so trace of that matrix is actually sum of all of the diagonal elements. But if you have something like Z, some of the diagonal elements is that same number. So it's much easier to compute trace of that thing because this is just that number of multiplication, dot product. instead of computing the entire matrix, which is n by n, and then summing the elements on the main diagonal. So this rule is very convenient for multiple different purposes. So what is determinant? Determinant is defined recursively, starting with the second order determinant, and then we go higher and higher orders of determinants. So we start with second order determinant. We have 2 by 2 matrix, and determinants defined only for square matrices. You do not have determinants for non-square matrices. For any square matrix, A1, B1, A2, B2, second order determinant is A1, which is Z element times Z element minus Z element times Z element. You just need to remember it. Okay. I can explain later what intuition behind determinant is, and there is meaning to why people invented it that way and not some other way. Okay. So this is definition of determinant of second order. And sometimes we write determinant as just 2 lines around the matrix A. Sometimes we write det of A. You have all kind of symbolics to identify determinant. But higher order determinant computation is based on the second order. So we need to define minor to understand how to compute it actually. We will not use that minor really, but you just need to remember what that thing is to compute the determinant, like how you compute the determinant. So let's say you have some matrix A, right? And you're crossing out column and row, same column and same row. Okay, for example, you're picking some ij, like row I and column j. You're crossing them out from the matrix. You have leftovers, okay, all of the elements which stayed in the matrix. You combine them together in n minus 1 orders matrix. So this becomes matrix of order smaller than the original matrix, right? Smaller by 1 in each dimension. Is it clear what I'm trying to say? Like you're crossing out 1 column and 1 row, and then you squeezing that matrix into smaller size. So the determinant of that smaller matrix is called minor of element aij. Okay, so you crossed i's row, j's column. The minor of that crossed thing is minor. Let me just give some example. Let's say you have matrix 1, 2, 3, 5, 6, 7, 8, 9. So let's say you are picking which element do you want? Which row? Second. Okay, we're picking that row. What column? Okay, second. Crossing that out, the matrix which is left is 1, 3, 7, 9. Right? All of these elements which are not crossed out. If you're doing determinant of that thing, this is minor of that element 5. So aij element is 5, which was your choice of row and column. So this is 5. This is the element. And the minor is practically 1 times 9 minus 3 times 7. So it's also number. All right? This is minor for element 5. And same thing you're doing for all other elements. So to compute determinant, what you need to do, you take in that element and you can develop it by row, by column, by whatever you choose. So you pick your row or your column, and typically you're choosing row or column where you have a lot of zeros, because then it becomes much, much easier to compute. Okay, so pick one with a lot of zeros. And then you're developing, for example, by first line. So you're taking first element, which is A11, crossing out element 1, 1, right? And writing minor of that element multiplied by that minor of element. Minus A12, minor of element 1, 2. Plus 1, 3, element, and so on. Pay attention that the signs are interchanging when you're going element by element. So it's like plus, minus, plus, minus, plus, minus, plus, minus, and so on, until you get to the end. And determinants are just minors that I just talked about for that particular element, which means that determinant of n by n matrix is practically minus 1 to the I plus j, which is a plus minus thing, times aij, which is that element by which you are crossing the line and column, times the minor of that same element. Okay? So practically, if some of these numbers are zero, you don't even need to compute the determinant. And pay attention that to compute z determinant, you also need to compute n minus one other determinants, developing, for example, by first row, first column, or second row, or whatever you choose. Okay, again, finding all these minors for that matrix now. So it's recursive kind of computation, and higher the order is, more complex it becomes. And this is why computation is very expensive operation to compute determinants. So before we get to properties, and again, I'm not getting into properties because we will not use too many of them, but I want to give you a little bit of insight of what it means, why people even use determinant. So determinant for particular two vectors is area of the parallelogram which they build as you sum them together. Which means if you have two vectors like that, that's in two dimensions. Okay, let's say you have two vectors, one vector, another vector. So their sum will look like that. This is their sum. Okay. So this is vector one, this is vector two, this is sum of the vector one and two. V1, V2, V1 plus V2. Okay, this is sum of two vectors geometrically. You remember from physics or whatever. Determinant is that area. This is what determinant is. Same thing in 3 dimensions, same thing in 4 dimensions. So determinant tells you the area of the parallelogram, which is built on these two vectors. Also, it means, for example, if determinant, like if you have some transform which is transforming particular vectors, right? Transforming particular space. If determinant of that matrix, transform matrix, is 1, this means that you are not scaling these vectors in anything. And practically you will do some rotation of the space and not scaling of the space. This is what determinant 1 means. You're not scaling your vectors. And I assume, have you heard about Jacobians and other things in calculus 2, 3, whatever, where you have that in integrals, you have exactly the same idea. People are just not getting that intuition behind it, because Jacobians is how much you squeeze or stretch your space in a way. And this is computed by determinant of particular derivatives of the space. But this is, I'm sidetracking a little bit. Okay, inverse matrices. Also very important topic. We will invert matrices a lot, okay, to solve equations typically. So people are used to divide by numbers or by variables or by whatever but not 0, right? We cannot divide by 0, but everything else we can divide by. Not in linear algebra. Forget about division. You do not have anything which is called division in linear algebra. What you have is inverse matrices instead, which means like dividing matrix A by matrix B makes no sense. This is nonsensical. You cannot divide matrices. Just cannot do that. Such operation is not defined, okay? But you can find such a matrix which is multiplied by the original matrix, will give you identity matrix. This is what you can do. So identity matrix, to remind you, is like all ones on the main diagonal, zeros everywhere else. So it's like 1 for us. Like in regular algebra, you have number 1. Here we have matrix I, which is identity matrix, right? So you can find such matrix A, which we'll call A inverse, A to the power of -1, which is multiplied by matrix A from left or from right. And these are actually different things except that case. Okay, so in case of matrices A, you can change the order. But if this would be matrix B, you can't multiply by A inverse from 2 sides and get the same thing. So this is how A inverse is actually defined. So this is such a matrix, which when multiplied by original matrix A, will give you I. All right. Not always such matrix exists. And this is how we differentiate between invertible matrices or not invertible matrices and not invertible matrices are called singular matrices. Okay, this is term for non-invertible matrices. And these matrices practically need to have some dependent rows, and we will talk what dependence means in linear algebra. They have linearly dependent rows or columns. So you have something which is proportional going on in the rows or columns of the matrix. Okay, you have some relations. Now, for 2 by 2, I propose to remember that by heart. We will do that like almost every lecture. I don't want you kind of to try to go to texts and to see like what that formula is every time. Just it's easy to memorize. To invert 2 by 2 matrix, you switch in the main diagonal elements, you put in minus on the other elements and dividing by determinant. That's it. This is inversion of 2 by 2 matrix. So to invert 2 by 2 matrix, you divide it by determinant, which is that AD minus BC. AD times BC is the determinant of that matrix. Okay, that's 1 divided by determinant. You're flipping these 2 values and you put in minus to the other 2 values. That's it. Relatively easy to remember. Okay, and we will use it a lot, so it's good to remember it. Any questions? For third order, it's obviously much more complicated, and you have some formulas for that. Typically, we use computer to invert matrices 3 by 3, but you can do that by hand as well, but it's more complicated. Here's one note which is very important here. Again, you cannot cancel matrices at all, but you can multiply from left or from right by inverse matrices. This is how you solve matrix equations in general. And since you'll manipulate a lot of matrix equations for state space, you just need to be aware of that you cannot just divide by A both sides of the equation. This is not how it works, but you can multiply by A inverse both sides of the equation, and then it will become I, like A inverse times A will become I, and I times anything is that anything, okay? Because multiplication of identity matrix by any other matrix is that other matrix. This is why it's so convenient for us, okay, to convert everything into identity matrix. It's very easy to multiply by that matrix. It's just like multiplying by 1. You're practically changing nothing, right? So this is why it is convenient. So let's see some simple example here. Let's say you want to simplify that thing and to find C as a function of all other elements in that equation. So you have that equation, AB squared, and B squared means basically B times B. Okay, this is just shortcut notation for multiplication of 2 matrices. And let's say this multiplication exists, so the dimensions are fine. Okay, all the dimensions here are okay. So you can actually do all of these multiplications. And this is not 0 number, this is 0 matrix of the appropriate dimensions. This matrix with all zeros everywhere. Okay, this is that 0. So how do we simplify that equation? How can we get C as a function of everything else? How we can take that C out somehow? So in regular algebra, you would be kind of canceling B and canceling A, right? And this is prohibited in linear algebra. You cannot do that. Okay, this doesn't work. But what you can do, you, for example, can multiply from left by A inverse here and there. So A inverse times matrix of zeros will be still matrix of zeros, right? It's not changing anything. A inverse times A will become I, which is identity matrix. A inverse times A will become I, so A will disappear, right? So it's like canceling, but not exactly, right? It's like the result is the same result, but this is the right way to do it, because in other cases, you will not be able just to divide by a matrix. There is no such thing as division by matrix. So you're canceling that matrix A by multiplying from A inverse here, and then you're multiplying from right by B inverse, okay? You would not be able to do that if it would be B squared A, for example. So then you would not be even able to solve it. In regular algebra, you can just cancel A and B, right? But if I would switch the order of A and B squared here, you would not be able to solve that equation at all, algebraically. But here I can multiply from the right by B inverse. So this will cancel the 2 here, it will cancel the B here. And what is left here is practically B plus C equals to 0. So now you can compute C, which will be equal to minus B, right? This is how you proceed. It just remembers that you cannot cancel anything ever in linear algebra. It's very important. How we solve system of equations? We will solve that again typically for eigenvalues. To find eigenvalues, we will need to solve eigenvectors rather. We will need to solve multiple systems of equation. Many of them will be second or third order, just to make it easier for computations. But here's how it goes. You have three different ways. First of all, Gaussian elimination. Remember what Gaussian elimination is? And we will not use it. But you typically learn that thing as the main thing in linear algebra. Spend on that maybe like 2 lectures to do Gaussian elimination. How does it work? Are you sure that you took a course on linear algebra? You will spend like 2 weeks on that out of the course. Probably those 2 weeks or maybe after introductory week, you get systems of equations. People kill you, like teachers kill you on solving systems of equations. So all linear algebra is about solving systems of equations, linear equations. I'm not even getting into like reduced echelon form, simpler than that. Though it's kind of same topic, but you can do the same thing with matrices. But I'm talking about equations right now. It's like high school stuff. So you technically take first equation, okay? You write one of the variables as a function of everything else. So you move everything else to the right side, okay? Let's say you have A11, X1, so you pick, for example, X1 variable, okay? So X1 equals 1 divided by A11, right? Times minus A12, X2, minus blah, 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 minus A1n, Xn, and plus B1. So you move everything to the right side, and you write X1 as a function of everything else, right? This is first step. Second step, you substitute that right long side into the second equation, third equation, everywhere like instead of X1, right? So the second equation will be not dependent on X1 at all, but will be dependent on X2, X3, X4, and so on, right? Do the same thing with X2, write X2 from the second equation as a function of everything else, and substitute that to all of the other equations, right? And they will depend only on X3, X4, X5, and so on, okay? Until you get to the last equation, it will be dependent only on the last variable, which is Xn. So you computed Xn and then go backward all of the steps, substitute Xn that you computed from the last equation to the previous equation, and compute the Xn minus 1, and then X minus 2, until you get to X1, which is headache, right? It's like a lot of manipulations that you need to do. And you have techniques to do that easier, like you think about that as like coefficients in the matrix, then you divide it by the first coefficient, you divide it all, like subtracting the first row from all of the other rows, like scaled row from the other rows to get like column of zeros below the first pivot number, and then you're doing the same thing for the second column, you're doing second pivot number, all of these techniques of reduced echelon row computations, okay? We don't need any of it. We have computers now. We are not doing by hand any of these computations. But we have inverse matrices now. So we can use inverse matrix to do the same thing. Let's say you have system of equation, which can be written like that. Matrix A times vector X equals vector B. This is exactly equivalent to that system of equations. Actually, the matrices were invented to solve that system of equations in the first place, historically. Which means that this is dot product of this thing by this thing, right? That's exactly what that thing is. Equals to the first element of B1. This is exactly the first row here. Second row is dot product of second row by that column, and equals to B2, and so on. This is exactly the same thing, right? So this matrix system of equations, this will give you exactly the same thing. How you solve that system of equations, which you write as A times X equals to B. You just seen it. Like you cannot cancel by A, you cannot divide by A. But what you can do, if A is invertible, and we will talk about conditions for that, you just multiply from left both sides by A inverse, right? So it will be A inverse times A times X equals A inverse times B. This is that thing, right? But this thing is I, and I times X is just X. So X equals A inverse times B. That's it. This is the technique. You just invert the matrix multiplied by vector B, which is a three coefficients. Done. Okay. No need in Gaussian elimination of anything. Here you have example. I mean, you can look through the example. It's just solving system of equations 2 by 2. So you're writing coefficients as a matrix. It's like 3, 4, 5, minus 7 is your matrix A. You invert the matrix, multiplied by vector of three coefficients, which is 3 and 0. And again, to invert that matrix, you just divide it by determinant, which is 3 times minus 7 minus 4 times 5. And you flip in these two values, and minus here and minus there. This is your inverse matrix. Okay, this is what you see here. This is determinant. And this is that matrix that I just talked about. Then you multiply that matrix by that vector, some algebra, and you get x1 and x2, which are solving that system of equations. This is how you do that by hand. Any questions? All right. So what is the meaning of solving a system of equations? For 2 by 2, it's very easy. Each row in your equation, like each equation, is practically equation of straight line. So more lines you have, more equations you have. Same thing, right? If you need to solve two equations with two unknowns, this is like finding intersection of two lines in two-dimensional space. And you have multiple different options. They might be parallel, and then you do not have any solution to that system of equations. They might intersect, and then you will have one solution to that equation. And this is where the matrix becomes invertible, okay, non-singular. Or they might be same line, which means same equation, maybe proportional equations. And then you have infinitely many solutions. You have many of them, as many as you want. Okay, so these are three types. But for 3 by 3 system, it becomes a little bit more complex. And obviously for more dimensions, it becomes even more complex than that. So if you need to solve 3 by 3 system of equations, then you have intersections of planes, and they can intersect in three-dimensional space in all kinds of ways, okay? So they might be all parallel, okay? Maybe one crossing two of them, so you might have two parallel planes and no common intersection. They might intersect at different points, and then you again have no solutions. Some of them may overlap, and others will be outside, but still parallel, so you have, again, no solutions. Here you might have one solution, which is actually rare, and you have one point where they all intersect somehow. You can have multiple or infinite number of solutions where they all intersect at the line, so they kind of same line. They might all overlap, which means same surface, same plane, and then you have, again, infinitely many solutions. Or two of them are together and third one is separate, and then you again have infinitely many solutions. So you have all kinds of configurations here that might happen, okay, in terms of geometry. Even for 3 dimensions, it becomes kind of tricky. So what we will do, we will separate between having solutions and not having solutions, or having infinite number of solutions. And this will be exactly the difference between having matrices with particular determinant, okay? So if determinant of that system matrix A is 0, then it's not invertible, so you have infinite number of solutions, or you have no solutions. But if it is invertible, which means you actually can do that operation here, okay? You can actually do that. You can find inverse matrix. Then you have single solution. And this will be that case. And this is the case we care about, to solve system of equations and to have particular solution to it. Not infinite number of solutions and not just no solutions. This is not that interesting. We are looking for that particular relatively rare case, but this is a case which is of interest to us. Okay, so this is geometric interpretation. And the last thing here is Cramer's rule. Also, instead of computing inverse matrix, for smaller order matrices, the easiest way is to use Cramer's rule. It becomes super difficult for higher order matrices, but it's very easy for lower order matrices, like second, third order matrices. For that, you just need to compute two determinants. It's ratio of two determinants. So what are these determinants? Each solution, which is an element x of your vector x, okay, is determinant of one matrix divided by the determinant of another matrix. So denominator is the determinant of your original matrix A. So if you kind of taking these coefficients, okay, from your linear equation, all of these coefficients is your matrix A, and this is vector B. So taking that matrix A, which is that matrix, and making determinant of that matrix. This is what that thing is. All right? Is it clear so far what that determinant is? Now, this matrix is special. This is almost matrix A, but you replace column J with vector B. So this is same matrix, same A. You just throw out column J and put instead column B and compute determinant of that matrix. This is that determinant. So the ratio of these two determinants, and pay attention to the determinant is just number. It's not vector matrix, it's just number, scalar number. So this is ratio of that matrix, modified matrix, divided by the original determinant. That's it. This is solution of your linear system of equations. You get same thing as inverting the matrix. So instead of computing matrices and I'll just take determinants. Very easy. Any questions? All right. So next time we will start talking about linear dependence. We will talk about eigenvalues and how you compute them, rank of the matrix. It's very beneficial that you will at least skim through that material before we get to that. Again, because I'm trying to put entire linear algebra course in 1 week. All right. And this is difficult, believe me. Like, not to skip multiple different things that you kind of supposed to know, but don't remember, obviously, from many years ago. So I'm trying to remind you a few things, but I cannot get into depth and to give you multiple examples and solving that by hand, because practice is the most important thing for linear algebra. When you're actually solving exercises, you are doing by hand all kind of computations, doing all of these things. They are very important, but you were kind of supposed to have them before. So I'm trying just to recap on what you're supposed to know. And that's why I'm running fast. Again, you are welcome to ask any questions or to stop me, or we can solve some problems in class. It's better to move slower with that course than to jump over and then you will not know what I'm talking about. Okay, when we get to the actual material. All right? Questions? Okay, thank you.